friends, welcome back, and we were discussing about the supercritical fluid extraction, wherein we have discussed the setup that is required for extracting the solid samples, and we also discussed about the industrial setup wherein continuity of the loading and unloading of the sample is of utmost importance. So now let's talk about when the sample is in the liquid form. Now if the sample is in the liquid form, we have a different type of extraction vessel wherein the sample, which is considered to be a dense material in comparison to the solvent, is introduced into the extraction vessel through the middle or from the top of the extraction vessel. And this is the major difference between the extraction vessel assembly of a liquid sample in comparison to that of a solid sample, because in case of solid sample the material is first loaded into the extraction chamber, which is then sealed, and then the solvent is introduced from the bottom. Though the solvent is introduced from the bottom in case of liquid as well, but the sample, which is the feed material, which is again the dense material, is also introduced simultaneously from the middle or from the top of the extraction vessel. So once the sample is introduced into the extraction chamber, either from the middle or from the top, the solvent, supercritical solvent, is introduced from the bottom of the extraction vessel. And the flow of the extraction solvent in comparison to the dense feed material is counter current, that is, they move in opposite direction, and this opposite movement or the counter current movement of the solvent with respect to the sample helps in extracting out the constituent by the solvent. And as rest of the process is same as that for the solid, the extract which is composed of the constituent as a vis-a-vis also the supercritical solvent, it is exited from the top of the extraction cell, and then it enters introduced into the separator where extract is removed and the solvent is recirculated back into the extraction vessel. Now in this image you can see the commercial grade counter current extraction vessel, which is also known as counter current column, and this column has a vessel has a approximate height of 10 meters. So this is a commercial setup for the liquid sample or the extraction of liquid samples using supercritical fluid extraction. Now whatever extraction vessel or whatever extraction setup we are using, we have to design that setup, we have to design that extraction vessel, or for matter of fact any vessel which is involved in this process, with respect to the requirement of the process, with respect to the requirement of the end product which we want from the process. Now for highly viscous sample, the extraction process further requires intensive and uniform contact between the feed and the solvent, and this happens also in case of solid material, and therefore sometimes we have to introduce certain mixers into the extraction vessels, and these mixers are largely used when the sample is in the form of viscous liquid. Depending upon the principle of the mixing, we can have mechanical mixers and we can have the nebulizing mixtures. Now mechanical mixtures can be further of two types. One is a mechanical in nature and second one is the magnetic mixture. Now as the name mechanical indicates, such kind of mixtures, they require a rotating shaft and the mixing pedals. Now the rotating shaft is normally outside the extraction chamber where it rotates, and this shaft then enters into the extraction vessels where pedals are attached, and these pedals basically provide the uniform mixing of the feed material with the solvent. Wherein in case of magnetic mixture, such kind of shafts are not required because they largely work on the principle of direct drum rotation. Now, this is the major difference between the magnetic and the mechanical mixers, because in case of mechanical mixtures, we require certain kind of bearings which will help in rotation. Lubrication is required, seals are required, belts are required which help in rotation of the shaft. And not only the components, but the maintenance of the components is also required. From time to time we have to lubricate the bearings, we have to replace the seals as well as belt in order to reduce the frictional coefficient. Lower the frictional coefficient, better is the torque generated by these mechanical mixture and better mixing is there. Whereas in case of magnetic mixture, as I told you, they work on the principle of direct drum motors. No belt, no bearings are required in order to rotate the shaft. These direct drum rotors, they generate a magnetic current which is used to rotate the shaft or rotate the pedals present in the extraction vessel. Another difference is these magnetic mixture, they do not achieve the high value torque that is achieved by the mechanical mixture. So if vigorous shaking or intense shaking is required, then mechanical mixtures are preferred. If normal mixing is required, then magnetic mixtures are normally used. Another technique of mixing is by nebulizing the viscous material through a nozzle onto the solvent or in the extraction vessel. Now, as you can, I will discuss this nebulizing process by showing you the image ahead. In this image, you can see the commercial grade mechanical mixture wherein viscous sample is mixed with the supercritical fluid with the help of this mixture. Once the sample is mixed with supercritical fluid, the viscosity of this mixture decreases and it further reduces the requirement of the torque values, thereby improving the overall mixing. Whereas this is a mechanical mixture which is designed to operate at a high pressure of 69 megapascals. Now, the second technique of mixing we discussed was by nebulization. So, as you can see in this setup, we have different types of vessel. Vessel 1 is largely used as a tank for the crude sample, which is highly viscous liquid, and this viscous liquid is taken up with the help of pump and the heat exchanger, which is indicated by number 3. So, this sample is preheated, taken up by the pump. It is then sprayed with the help of a nebulizing nozzle onto the solvent, which is again sucked from the vessel which is labeled as 9, and from there it is introduced into the extraction vessel. The sample is introduced with the help of nebulization, which help in the uniform distribution of the sample into the extraction solvent, which further improves the surface area of contact of the sample with the solvent and thereby improving the overall extraction process. Now we move on to the instrumentation aspect of the supercritical fluid extraction. In order to design an instrumentation or in order to design an equipment for supercritical fluid extraction, we have to keep in mind certain ideal characters for that particular process. The equipment, whatever we are designing, it should be safe, it should not jeopardize the whole process, and not only the process but also the operators which are operating those systems. The equipment should be easy to handle and easy to maintain. When we talk about easy to handle, then it means the loading and unloading of the feed material should be quite easy. The cleaning of the vessels, whether it is an extraction vessel, whether it is a separator, whether it is a heat exchanger, so cleaning process should also be easy. As you have seen in different figures that the supercritical fluid extraction unit is nothing but it is a complex arrangement of different vessels that are connected through various tubings. So the connection part of that equipment should also be very simple and should be easily maintained. Then last but not the least, it should be easily replaceable. When I talk about replaceability, it means whatever parts that have been damaged or the spares we want to replace, we can easily replace them. Such kind of characters are to be there in an ideal supercritical fluid unit. Another important aspect is the handling of pressure and temperature conditions. We know that supercritical fluid extraction takes place at a very high temperature and pressure conditions. So whatever instrument, whatever equipment we design, it should be able to withstand those high pressure and temperature conditions. It should be economically viable. As you have seen in different pictures, that huge setups are required for setting up a industrial scale supercritical fluid extraction unit. So whatever extraction unit you are designing, one should always keep in mind the economical viability of that unit. This is one aspect. Second, the unit should be energy efficient, because this efficiency in terms of energy usage will also be reflected in the economical viability of that process. Lesser consumed energy, you are saving a lot of cost on the energy aspect, which will again help in making the process economically viable. Now, as we have seen in different images in some of the previous slides, there are various components that are involved in setting up this unit. And these components are the storage tanks for the carbon dioxide, which is used as the solvent in supercritical fluid extraction. So in simple words, we can say the unit requires a storage tank for the solvent. Then it requires various types of vessels, and these vessels are used for different purposes. They can be used for extraction, and we call them as extraction vessels, where extraction takes place. Then we require separation vessels, where separation of the constituent from the solvents take place. Then we require vessels for collecting the product, which we call them as product vessels. And we also require certain circulating vessels, wherein the solvent is recirculated back into the extraction vessel. So different types of vessels are also required in supercritical fluid extraction unit. Third component are the pumps and the compressors. And pumps and compressors are considered to be the heart of the supercritical fluid extraction unit, because these are the units which helps in maintaining the pressure conditions required for the extraction. And there are different types of pumps that are available in the market, though the designing of the pumps is very limited, but the manufacturers have their own proprietary designs for the pumps and the compressors. Another important component of the unit is the heat exchanger, and heat exchangers are largely used to maintain the temperature conditions throughout the process, temperature conditions of the solvent, temperature conditions for the extract when they are introduced into the separators. So as we discussed, that these heat exchangers help in altering the thermodynamic conditions for an extract, which further helps in their separation from the solvent. So the heat exchangers should be designed in such a manner that the cleaning process, because the solvent is gas, so its residue will be hardly left in the heat exchanger. The residues that will be left will be of that of the constituent or the solute molecules. So the cleaning aspect of the heat exchanger should be quite simple. Then valves and pipings are also used in a supercritical fluid extraction unit. Different types of pressure regulating valves, flow regulating valves are used in order to maintain the proper flow of the solvent, proper flow of the extract, in order to maintain the proper pressure conditions. Many times you require to cut off one vessel from rest of the process, as we discussed in the industrial setup, wherein once the extraction was complete in the first vessel, it was then cut off from the rest of vessels, then loading and unloading of that vessel takes place. So these valves and pipings which connect the different vessels, which help in circulating the solvent from the separator back to the extraction vessel. So all these components are of great importance while designing a supercritical fluid unit. And last but not least is the control systems, the systems which control all these components in tandem, in rhythm, because if any of the component is out of the synchronization along with the other components, the whole process can collapse. So the control systems largely composed of various sensors which can sense the change in the pressure conditions, which can sense change in the flow conditions, which can sense change in the temperature conditions. And various sensors are placed at different areas of the unit, such as pumps are there, compressors are there, heat exchangers are there, extraction vessels are there. So if in case there is any kind of non-required change in the pressure or temperature conditions, these sensors can set an alert in the control systems, by which the controller can easily manipulate those conditions, which can easily control the altered condition in order to make the unit continuously functioning. Now we will discuss all these components in detail. So coming on to the vessels. Now the extraction vessels, as we discussed, that the technique involves high pressure and temperature conditions. So vessels should be able to withstand the operational temperature and pressure conditions. Whatever the conditions of pressure and temperature are there, vessels should be able to withstand them. And these vessels can be extraction vessels, these can be separating vessels, these can be product vessels. Obviously, product vessels need not to be rigid enough in order to withstand the operating pressure conditions, because the product tank will be at the atmospheric pressure. But yes, extraction vessel where the pressure and temperature conditions are above the supercritical value, they should be able to withstand those pressure and temperature conditions. Further, the pressure and temperature conditions vary with the use of the vessel. If it is used as a separator, then it requires different pressure and temperature conditions. If it is a product tank, as I told you, it does not require to withstand any high pressure or temperature condition. So depending upon the use of that vessel, one has to design that vessel in order to withstand the operational temperature and pressure conditions. These vessels can be made up of either stainless steel or carbon steel. Now carbon steel is nothing but an alloy which is mixture of carbon and other elements like manganese is there, steel is there, iron is there. So there are different types or grades of carbon steel depending upon the percentage of carbon that is involved. Now carbon steel, though it is very costly, it is becoming material of choice because it is very hard and rigid, and it can withstand a very high temperature up to say 800 degrees Fahrenheit. The only problem with carbon steel is, since it's very rigid, ductility is very low in carbon steel. Sometimes such kind of the material made up of carbon steel is vulnerable towards cracking when extreme conditions are when it is exposed to extreme conditions. But still, it is becoming material of choice for establishing supercritical fluid extraction units. But one has to keep the cost factor into mind. By and large, as of today, stainless steel is largely used. Now, if stainless steel, as I told you, it is now largely used, thickness of the steel that has to be used is very critical, which makes the vessel able to withstand the operational temperature and pressure conditions. And thickness of any part, whether it is a vessel, whether it is piping, whether it is the separation vessel or a storage tank, thickness of the steel that is to be used in preparing that vessel can be calculated by von Mises equation. So as you can see this equation, where Pi is the internal pressure, K is the external to internal diameter ratio, sigma is the stress, and SF is the suitable safety factor, which is generally 1.5. Now as you can see that the pressure conditions or the thickness of a stainless steel sheet that has to be used to prepare a vessel or piping is also dependent upon the internal or the diameter of the vessel or the piping that has to be made up of that stainless steel sheet. I have taken an example wherein a cylinder, thick walled cylinder vessel is having an internal diameter of 200 millimeter, is prepared by stainless steel as well as carbon steel, and this vessel is exposed to different pressure conditions. Now as you can see, as we increase the pressure conditions, the thickness required to prepare the vessel either from stainless steel or for carbon steel changes. Though the thickness for carbon steel is much less in comparison to stainless steel because of its rigidity. So as you can see, when the pressure is at 100 atmosphere, stainless steel requires a thickness of 8.1 millimeter, whereas carbon steel requires a thickness of 4.6 millimeter, almost half the value of stainless steel. And when the pressure is increased up to 300 atmosphere, the thickness of stainless steel sheet required is 32.7, whereas as that of carbon steel it is only 16.2 millimeters. So this is how, with the change in pressure, keeping the internal diameters constant, we can calculate the thickness of the material that is used to prepare the vessel can be calculated. Now most of the vessels, whether it is used for separation, whether it is used for extraction, whether it is used for storage, they have two openings, and they are largely on the upper and the lower side, and therefore they have two closing systems or the closing lids. Now this closing system is largely automated, because in order to save the time factor in terms of opening and closing of the system, because these systems operate at very high pressure and temperature conditions, so if you have to close and open system manually, lot of efforts and time is required. So in order to save on time, majority of the opening system and the closing system at industrial level are highly automated. And there are two different types of closing systems that are seen in the industrial scale. One is the ring closure systems and other one is the clamp closure systems, and in this image you can see the ring closing system in the picture A and clamp closures in the picture B. Now ring systems are nothing but a metallic ring is there having appropriate diameter as that of the extraction vessel, and this ring is fitted by applying pressure from the above, and it fits into the extraction vessel, thereby blocking any kind of leakage. Whereas the clamp system, clamps are on the outer side of the vessel, which helps in tightening up the closing lid with the extraction vessel. In this image you can see the industrial setup of the ring closing system. You can see all the three extraction vessels have a ring closing system, and they are fully automated, controlled by the controller system. So whenever the one has to open the system, you just have to press the button, or you can set up the timers in the control system. So once the extraction is complete, they are automatically open. Once the extraction has to start, they automatically get closed. So you save lot of time and efforts in opening and closing of these extraction vessels. Now whatever vessel we are using, the vessel should be designed in such a manner that we should focus on the ease of cleaning of the vessels between the charging and the emptying of the vessel with the feed material. Because after the extraction is complete, we have to remove the exhausted feed material, we have to clean the sample, we have to clean the vessel before we have to charge the second batch of the feed material, which can be same or which can be a different material. If a material is different, then we have to clean the extraction vessel completely. If the same material is used, we can skip the cleaning part, but we have to empty and refill the extraction chamber. So the ease of emptying and filling the plant matrix or the powdered material or the feed material should be there whenever you are designing a extraction vessel for supercritical food process. Shape of the vessel and its aspect ratio must also be carefully designed, and one has to keep in mind that the vessel shape and size should be designed in such a manner that it reduces the efforts in handling that extraction vessel. So you don't require a special effort to handle that extraction vessel, and efforts is required in terms of emptying and loading of the charged material or the cleaning of the vessel. Further, all these parameters should be kept in mind and should be considered, keeping the overall cost that is involved in designing the vessel. So cost factor is also important whenever you are designing different vessels for the supercritical fluid process. Now, as I told you that different vessels are made up of made for different purposes in this whole process. Extraction vessels are for carrying out extraction. Separator vessels are to separate the constituent from or the solute from the solvent. Storage or the product vessels are to collect the solute molecules. Storage vessels to store the solvent or co-solvent. So every vessel has different use, and not only use, they are exposed to different pressure and temperature conditions. So for extraction, keeping in mind their usage, keeping in mind the conditions to which they have to be exposed, one has to design the vessel. If you are designing a vessel for extraction purpose, then the steel or the material you are using, it should be of appropriate thickness so that it can withstand the high pressure and temperature conditions. We know that separator vessels operate at a pressure and temperature conditions lower than those of the extraction vessels. So accordingly, we have to select the thickness of the material that is used to design the separator vessels. Product tanks or the solvent tanks, they further store the material at pressure and temperature conditions far lower than required in the extraction or separator vessels. So accordingly, we have to select the thickness of those vessels. So the bottom line is, so whatever vessel you are designing, you have to keep in mind the usage of that vessel, the conditions to which that vessel has to be exposed. Next component is the pumps and the compressors. So as I told you that these are considered to be the heart of the extraction unit, and different types of pumps and compressors are used. Friends, we will discuss the designing of the pumps or different types of pumps and compressors that are used in supercritical fluid unit in my upcoming lectures. So till now we have started with the historical background of the supercritical fluid development. We discussed about the principle of extraction, different types of the solvents that can be used, properties of those solvents. Then we discuss about the supercritical fluid process. What are the different types of processes, different steps that are involved in the process. Obviously, supercritical fluid extraction process can be static or dynamic like other extraction techniques. In static, as the name indicate, the feed material and the solvent is exposed to the desired pressure and temperature condition for specified period of time, and once the extraction is complete, we remove the exhausted material, we charge it with the fresh material. Whereas in case of dynamic mode, the solvent flows through the feed bed continuously at a specified flow rate, and as the solvent is flowing continuously through the material bed, the material particles come in contact with the fresh solvent every time. Saturation does not occur, extraction yield increases. So if in comparison, if we see static and dynamic mode have better extraction yields, but again one has to be very careful in designing such processes, taking into consideration the cost factor. Dynamic processes are always costlier than the static processes. Then we discuss about the components of the supercritical fluid unit, and in the end we discuss about the vessels that are used in the supercritical fluid extraction unit. Thank you.